Hi, Chem 151 students. We're now in week 4, so we're going to be covering the second part of the Kinetics chapter, chapter 16. Now, this week is a little bit shorter than most weeks because we're starting on Tuesday. We had a holiday on Monday, Labor Day. And so you will find that everything's a little bit shorter. There are only 2 lectures this week instead of 3, and the homework set is a little bit shorter. You'll have one experiment due, experiment 1. And you'll also be working on other things this week as we start to come into lab. For our lectures, we're going to have 2 lectures. One will be about kinetic theory. The first one, that's lecture 4.1. The next one that we're coming up on will be on reaction mechanisms and elementary steps. So the steps that occur within a reaction that drive the kinetics of that reaction and how we can explain the kinetics of that reaction. So let's start with kinetic theory, which is all based upon the collision of the particles that are undergoing reaction, be they molecules or atoms. So the basic principle here is that for molecules to react, they must collide. They must hit each other. And if we increase the concentration, that is one way of making those molecules hit each other more often because they're going to be packed in closer together and more likely to hit each other, and so this will increase the reaction rate. It's important to note that the number of collisions depends on the product of the number of molecules. This is why we multiply the concentrations in the rate law. And so instead of adding them, you may have wondered that if we have, more of this other reactant, if we have twice as much, we'll have twice the reaction speed because we're multiplying here. Let me show you what I mean with a picture. So if we're looking at a very small system here with just 4 molecules, okay, of reactant A and reactant B. Well, this reactant A molecule can collide with this reactant B molecule or with this one. So there's 2 possible collisions it can undergo. This one can also collide in 2 ways. So altogether we have 4 possible collisions here. Now if we add another reactant molecule A, now we don't have 5 possible collisions. We don't have 1 more possible collision. We actually have 2 more. We have 3 times 2 or 6 possible collisions because each reactant A molecule can undergo 2 collisions, one with each of the reactant molecules B here. So you have 2 green lines representing 2 possible collisions, 2 red lines and 2 blue lines. Altogether that's 6 possible collisions. If we add another molecule, molecule B here, now we have 3 reactant A molecules times 3 reactant B molecules, 9 possible collisions. This reactant A can collide with any 3 of these reactant B, likewise for this one and likewise for this one, so 9 possible collisions. And so that's why the rate law is described by multiplying the concentrations. If we imagine the concentration here of A being 3 in this case and the concentration of B being 2, then the product here is going to give us the likelihood of collision, or 6 in this case, or 9 in this case. And so that explains the part of the rate law that has concentrations in it. It doesn't explain the K yet, and we're going to get to K. We're going to talk a lot about the rate constant K. Also important is the structure of the molecule that's undergoing a reaction, because if a collision is going to result in a reaction, that collision must happen it must not only happen, it must happen with enough energy, meaning those molecules must hit each other hard enough or fast enough. And they must be in the right orientation so that old bonds can be made while simultaneously, old bonds can be broken rather, while simultaneously new bonds can be made. And so this property is wrapped up into the rate constant, or K. So the rate constant itself can be described by a mathematical equation. It's this one here, which is called the Arrhenius equation. It says the rate constant equals A, and A is called the Arrhenius factor, or the frequency factor, times E, the base of the natural log, to the power of the negative of the activation energy over R, which is the ideal gas constant but stated in joules, as we'll see, divided also by the temperature, and this temperature must be in Kelvin. So what is this A that we see here? So the A can be kind of broken up into two parts. So it's the product of the collision frequency, which is indicated as Z here, times the probability that if the collision happens, it will happen in the correct orientation so that the molecule will undergo a reaction. So these molecules are always flipping and spinning around. They have to hit each other in the right way to undergo this reaction. So the A gives you the frequency of a collision that is in the correct orientation. Then after that, the rate constant is determined by what's known as the activation energy and the temperature and this ideal gas constant. So let's break this down a little bit further. Right now we're focusing on this frequency factor. So P here just depends on the way that the molecule is arranged. All molecules have different shapes and they need to hit each other in a particular way in order to react. So the orientation probability, it depends on the shape and the way that the molecule is structured. What about the rest of this? The activation energy, the temperature. Let's break this equation down further into each of its parts and talk about them more. So this is the Arrhenius equation. A again is called the frequency factor, so we just discussed this. It represents the likelihood of a successful collision at the right orientation. E is the base of the natural log. Its value is 2.71828, and it goes on and on. R is the thermodynamic ideal gas constant. So you may be familiar with the ideal gas constant. This one, 0.0821 liters times atmospheres over moles times Kelvin. These are actually the same constant, but this one is expressed in joules instead, and this is going to be the one you want to use for our discussions here. If you forget which one to use, just remember, just think about your units, and I'll show you how to think about this as we do the problems. Activation energy is an energy. It's going to be in joules, so we need a constant that also has joules in it. T is going to be the temperature in Kelvin units. And then we're going to go into more detail on the activation energy in a little bit. But it's really important that the temperature is in Kelvin units. It has to be in Kelvin units because you can see our gas constant is in Kelvin units, and because Kelvin units are a temperature relative to absolute zero. And the temperature here, remember, is telling us about the speed of the molecules. And so if we want a measurement of the speed, we have to use Kelvin units, because 0 Kelvin is 0 speed, and then faster and faster as we go higher. So we'll always use Kelvin units for this. Oops, that's behind my head a little bit. But here's a picture that shows the difference between a effective collision in the correct orientation versus an ineffective collision. So in this reaction, the NO molecule is reacting with NO3 in order to make NO2. And this is a reaction that happens all the time in the skies above our heads, with lots of cars around here spitting out NOs. They call it NOx, NO, NO3, NO2. And in the atmosphere, these various molecules undergo all kinds of reactions all of the time. And so NO2 is kind of smoggy stuff. So we can see here what needs to happen is that one of the oxygen atoms needs to go from the NO3 over to the NO, right? And it's got to be attaching itself to the nitrogen atom. So in this example here, in this diagram, the blue is the nitrogen atom. So the blue one's here, the nitrogen. The red ones are the oxygen. And so this collision is ineffective because this oxygen atom wants to get over here. And so you cannot begin to form this bond if the oxygen atom is hitting the other oxygen atom. They're not going to bond with one another. It will also be ineffective if this oxygen atom is hitting this nitrogen atom. That's not what we want. We want one of these oxygen atoms to attach over to this nitrogen atom. Now, if this molecule flips around, because they're always flipping and turning, if the nitrogen atom hits the other nitrogen atom, that's not going to be an effective collision either, because we need this nitrogen atom to be hitting one of these oxygens. So here, when it's coming this way, it's hitting one of these oxygens, but it's not hitting it in the right place. The oxygen is going to want to attach more in this area. It's too close to this other oxygen here. So an effective collision would be one like this. The molecule hits right in the spot where the oxygen would want to attach to the nitrogen here. So that by this collision, the oxygen can pop off this nitrogen and pop on to this nitrogen over here. And the result is two NO2 molecules. And so this shows you where that frequency factor comes into play. This frequency factor is giving us the probability that a particular collision will occur in this fashion so that the reaction can go ahead and continue. All the rest would be these ineffective orientations. So that frequency factor tells us all about the ways in which they might hit each other and the probability that they will hit each other in the correct way in order for a reaction to be possible. Now, the rest of this has to do with actually having enough energy to react. And so that's where we get into transition state theory. So, an effective collision between the particles leads to the formation of a transition state. If it's high enough energy and the correct orientation, it will make a transition state or an activated complex. And a transition state is kind of an in-between between the reactant molecules and the product molecules. It's a situation where the bonds that need to be broken in the reactant molecules are starting to be broken, and the bonds that need to be made in the product molecules are starting to be made. So that involves partial bonds. And it's a transitional species, and it's usually very, very short-lived. It doesn't stick around for very long. It's very high in energy. It's unstable. And so it will immediately go and make the reactants or go and make the products rather, or return to the reactants. And I'll show you what that looks like in a picture on the next slide. So this transition state is a very, very high energy state, but the set of reactants need to get to this state in order to possibly make the products. The energy that's required to form this transition state is referred to as the activation energy, and that's the one that was EA in the equation. So what does a transition state look like? Well, here we have a molecule that has a bromine attached to a CH3, and so that's what we have in this picture. And what's being produced is a bromide ion, which is going to come off here, and methanol, where this oxygen will be attached to this carbon. So this transition state is the highest energy in between for this reaction. It's what happens right in the middle of this reaction. And you can tell it's halfway between the bromine being attached to the carbon and the oxygen being attached to the carbon. These dashes are representing partial bonds. This bond between the bromine and the carbon is halfway broken, and it's going to break. This bond between this oxygen and carbon is halfway made, and it's going to form. And so right now we're at this transition state, and this is what a transition state looks like. You can represent this just if I were to draw this on a piece of paper. It's very difficult, you do the best you can. But I might draw bromine dash 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 to carbon, and then I put an H here, and then I could use wedges and dashes if I want. If I use a dash like this generally indicates going back into the page. So that would be this hydrogen here going back into the page. And then if I use a wedge, that is often used to indicate something popping out of the page. And so that would represent this hydrogen popping out of the page. And then I could have another dash bond here to oxygen, which is bonded to hydrogen. And so that would be this part right here. And so it's difficult. I don't usually expect you to, be able to draw in 3 dimensions like this, but you should be able to kind of visualize what this is like this. Let's give a more detailed look here. So at the very beginning, so here what we have on the bottom is what's referred to as an energy diagram. Okay, and so we're going to go into that in a moment, but what I want to point out is that at the left side of the energy diagram, we have written our reactants here with a line over them. This is the methyl bromide, which is this guy right here. So it's got bromine, which is this orange one, attached to the carbon. And these guys are about to collide in the correct orientation where the oxygen is going to hit the carbon here. Okay, and now we started the reaction, and we're starting to go up to higher energy. So that's what this line means here. We're going to a higher energy state. So this is the higher energy state represented right here. We're almost to the highest energy transition state. And the bond to the bromine is starting to break, and the bond from the carbon to the oxygen is just beginning to form. Then when we're halfway through the reaction, we're at the transition state, the highest energy point. And so now we can see that the bond between the carbon and the bromine is basically halfway broken. The bond between the oxygen and the carbon here is halfway formed. So we're at the middle point in this reaction happening. Then we start to go to a lower energy point here. So we're going down this energy diagram here. And now the bond between the bromine is almost completely broken, and the bond between the oxygen and the carbon is almost completely formed. And then finally we get to the products. The product here is a bromide ion, and the other product is the methanol. And so those are written right there. This diagram at the top here is showing the relative distances between the bromine and the carbon. So here the bromine and the carbon are close, the oxygen's far away, then the carbon's almost halfway between them. Now the carbon's basically halfway between them. Now the bromine's moving away, the oxygen is close to the carbon. Now the bromine's completely separated, and the carbon is bonded to the oxygen. So this can be also written, as I mentioned, with with these wedges and dash structures, as we see here, like this. These are just a paper representation of this 3-dimensional model. And now let's talk about how all of these concepts relate to an energy diagram. So in your problems, I will ask you to draw energy diagrams. So on the vertical axis here will be what's known as the potential energy. So you can think of the potential energy, I always think of it like a ball on a hill. So or in your hand, if you lift up a bowling ball, it has more potential energy because it's been lifted up. If I put it here on my desk, and that potential energy can be released as kinetic energy. If I push it off the side of the desk, it will fall to the ground and release a lot of energy, right? That potential energy is due to gravity. Here, the potential energy is due to the electrostatic attractions between atoms. So the attractions between positive and negative parts of these molecules here. And so we can see that overall in reactants and products, there can be different potential energy, just like the ball at the top of my desk has different potential energy than the ball at the bottom. And so our reactants in this case have a greater potential energy. It's like they're at a hill. But notice there's a hill on the way. So this ball here, let's say there's reaction to the ball, they're not just going to be able to fall down this cliff because there's a hill in the way. They need to get over that hill. And the hill is the activation energy. So that is the energy required to take the reactants and give them enough energy in order to create the transition state, which is represented by the top of this hill. Once we've given these molecules enough energy, then they'll roll right down. They'll either roll backwards and go back and make what they had before, or they'll roll forwards and they'll make the products. And once they make the products, they'll settle into this valley of lower energy. And so you'll notice that this reaction could also go backwards too. If this reaction were reversed, these products would go backwards and make the reactants, which can totally happen. So that's going to be something we're starting to talk about in this chapter, is that reactions can go backwards. They can go in reverse. And that's going to lead us into our next topic for starting after the exam 1, which is going to be equilibrium. But notice that in order for this reaction to go backwards, again, these molecules right here, these particles, must get enough energy to reach a transition state to go backwards. And so you'll notice that in this reaction, the activation energy for the products to go backwards and make the reactants is greater than the activation energy in the forward direction for the reactants to go and make the products. And this is because this is an exothermic reaction. I can tell this is an exothermic reaction because my reactant molecules have greater potential energy than my products. So along the way here, when my reactants make products, energy is lost. And that energy that's lost is the delta H of the reaction. Oops. Here, so the delta H of the reaction. So that delta H is negative if you have an exothermic reaction, so we can see it dropping down here. If you have an endothermic reaction, it will be positive. And so let's do a little bit more practice here. I'll have a practice problem in a moment to draw an energy diagram and label all these parts. So when I ask you to draw a potential energy diagram, this is what I'm looking for right here with all these parts labeled that you see here. So in order for the reaction to the collision to be effective, it must not only be in the correct orientation, but it must have enough energy. It must have the energy that is equal to the activation energy in order to create the transition state. So if molecules are hitting each other too slow, there won't be enough energy to react. They must hit each other pretty hard so that the old bonds can begin to break and the new bonds can then begin to be formed. So when particles collide effectively with enough energy, they reach the activated state or the transition state. And this energy that is required is referred to as the activation energy, or E sub A. If an activation energy is low, that means the reaction can go fast. More of the molecules will be able to have an effective collision. So a smaller activation energy will mean a larger K, which will mean an increased rate. Let's break this down. What if you forget this? Oh, what if I forget? Do I have to memorize this, Dr. L, right here? No, because I'm going to give you this equation. Hopefully you'll know it, but you don't have to. You could just look it up. No big deal. But you should be able to look it up and interpret it. And so let's look at the way the math works for this. So this is e to the negative power. Okay, and so what this means is that as this number gets bigger, this whole exponential gets smaller. Think of like this. What is a bigger number here? 2 to the minus 1 or 2 to the minus 2. Let's use simple numbers. Well, this is 1/2, and this is 1 over 2 squared, or 1/4. So you can see that when the exponent, the negative exponent, becomes a more negative exponent, then the value becomes smaller for the exponential overall. That is true here too. So if the activation energy gets bigger, this whole exponential value gets smaller. So a large activation energy will mean a small k, but a small activation energy, smaller here, smaller negative number, will mean a larger k, and that means a faster reaction here. I very highly encourage you to work through that mentally. Plug in some numbers in your calculator if you like. Change the EA from 1 to 2 and see what happens. You should get a feel for the way this math works. You don't want to memorize this. You want to have an understanding of the mathematics that tells you when this negative exponential gets bigger, that means my whole value for the exponential is smaller. So a bigger activation energy means a smaller K. And a smaller activation energy means a larger K, which means a faster reaction. So just like this high jumper here, if he does not hit that bar, if he doesn't make it over, it's a failed jump, right? And it does not give him any points, okay? The same is true for these molecules. If they hit each other with enough energy to get here, it's not enough. They'll just fall back down and make reactants. They have to hit each other with enough energy to get to the activated state and make the transition state. Then they can go and react and make the products. So in this reaction, we can see that it's exothermic because the delta H is negative. The reactants have more potential energy than the products. So as a result, the activation energy in the forward direction is smaller than the activation energy in the reverse direction. In an endothermic reaction, the opposite will be true, and I'll show you an example of that. So here are two examples. On the right side, we have another exothermic reaction. Here, we can tell because the reactants have greater potential energy than the products. And so there's a negative delta H reaction, and the result is that the forward activation energy is lower than the reverse activation energy. This reaction will go faster in the forward direction than it will in the reverse direction, assuming we have equal amounts of reactants and products. Now, the opposite is true for an endothermic reaction. So we can tell this is an endothermic reaction because the reactant molecules have lower potential energy than the product molecules. We got to drag these guys up to the cliff, basically. This is me pulling the bowling ball up to my desk right here. But in order for the reaction to happen, we first need to hit the transition state. So the transition state isn't down here, it's way up here. So for these reactant molecules to react, they must hit each other with enough energy to get all the way up to the transition state. And then they can go on and react and make the products. And so we can see that if the reaction is endothermic and the products have greater potential energy than the reactants, then the forward reaction will have a higher activation energy than the reverse. And in this reaction, we have two NOCl molecules reacting to make NO and Cl2. And so we can see here when so this is one NOCl molecule, this is another. When they hit each other, the bonds between the nitrogen and the chlorines begin to break, and a new bond between the two chlorine atoms is formed. This is the transition state, halfway. So that these bonds are halfway broken, and the chlorine bonds for the Cl2 are halfway made. In this reaction, NO is here, it's reacting with ozone, O3, which is a real reaction that happens in the atmosphere. And in this reaction, the bond between the two oxygens is beginning to break here, and a new bond between this nitrogen and oxygen is beginning to form. This represents the transition state. So here's another reaction that's very important in the upper atmosphere. It's ozone reacting with oxygen atom to produce O2. And this is one of the purposes of ozone. So ozone is basically like a free radical scavenger, meaning that it will react with very reactive atoms in the atmosphere and get rid of them, which is good because we don't want to be breathing those because they will react with our own molecules. So it kind of cleans up the very highly reactive molecules out of the atmosphere and produces oxygen. So here we see we're given a bunch of information. We see that the activation energy in the forward direction is 19 kilojoules. Delta H for the reaction is negative 392 kilojoules. So the negative here means that because this is negative, right here, negative, this is telling us we have an exothermic reaction. A negative delta H is exothermic, a positive delta H is endothermic. It says draw an energy diagram and predict the structure for the transition state. So we would write our energy diagram, we'll make it here, and this is going to be the potential energy, which it will be in joules. And then here we have what's known as a reaction progress or reaction coordinate. And then, so now we're going to put our reactant, we're going to put a line here for our reactant molecules. So our reactant molecules are O3 and O. And first we should figure out, too, this is exothermic, right? So our reactants will have more energy than our products. And let's see, yeah. Okay. So, and our reactants are going to be the O3 and the oxygen. And our products are going to be 2 oxygens. And this distance right here, this is the delta H of the reaction. This is the negative 392 kilojoules. Now our activation energy is only 19 kilojoules. So when we draw our plot here, it's going to be a very small hill, because this whole delta H is negative 392. So 19 is going to be small. So I'm going to do my best to draw it to scale, but it's going to be a very small hill, this one. Woo. Oh, let me get my eraser out here. Okay, let's try that again. So I'm going to draw a little baby hill. And then it's going to go, okay, like that. All right. And so now we can label the rest of it. So our activation energy for the forward direction is going to be this value right here. And so I'm gonna like do my label out here. This is the activation energy in the forward direction. And because this is exothermic, the activation energy in the forward direction is smaller than the activation energy in the reverse direction. And this right here, whoops. Let me erase that. And did not draw that correctly. Okay. So now for our activation energy in the reverse direction, again, this is going up to this level right here. So our activation energy in the reverse direction is going to be from products here all the way up to the transition state. And this is going to be the activation energy in the reverse direction. And right here, this top of this is the transition state. And often the transition state is indicated with this, like that. This is transition state. Or the activated complex, or it's called a lot of different things. Transition state, activated complex, activated state. There's quite a few different names for this, unfortunately. Now, in terms of a transition state, what we could draw here is the oxygen. So this is going to be like this, and this is ozone right here. It's going to have another oxygen here, and then there's going to be an oxygen atom. And what's going to be happening in this reaction is we're going to have a partial breaking. So this bond will begin to be broken, and then there will be a new oxygen atom here, and this bond will begin to be forming. And so in the end, this bond here will break, and this one will form, and we'll have two O2s. So it'll actually be a double bond here. And so if we look at the next slide, that I've just got that all typed out here. One other part of the question was, what is the reverse of the activation energy? So the reverse of the activation, or the reverse activation energy, is going to be equal to, we can see the delta H of the reaction, which takes us from here to here, and then plus the activation energy, which is going to take us from here to here. So the activation energy reverse is going to be the 392 kilojoules plus the 19 kilojoules. So it's going to be 411 kilojoules, and this is positive because it's the energy that you need to put in to get from these reactants here to these products. So and so this is just a drawing of the same thing here that I did. Okay, so there's one last thing we have to talk about now, and that is the temperature. So how is the rate constant going to vary with the temperature? Well, you might have noticed if you ever left a gallon of milk out of the fridge, that if you leave it out for a few hours, it's going to start to smell funky, right? But you can leave it for a couple weeks in your fridge. The difference there is the temperature. All the biochemical reactions and this bacteria that are eating the milk go way faster when it's just a little increase in temperature. So temperature has a huge effect on the reactions. So for many reactions, if you increase the temperature by 10 degrees Celsius, it will double or triple the rate. If you're taking milk out of the fridge, you're increasing it by probably 20. So you're really increasing the rate of spoilage really fast there. So experimental data shows K increases exponentially as T increases. This is described by the Arrhenius equation, which is exponential. So again, here K is the rate constant, A is the frequency factor, EA is the activation energy. And analyzing this again mathematically like we did, if we have a bigger temperature here, that is going to make this entire negative value smaller. And so that will make, so let's break this down. So again, if we increase the temperature, that is going to decrease EA over RT. It will make it a smaller number. So we'll have a smaller negative number here, which is going to increase E to the minus EA over RT, which is going to increase the rate constant. And so you'll get a faster rate, right? Because the bigger the T, the smaller this fraction, so the smaller of a negative number we have, so the bigger this exponential is, and thus the bigger K is. Again, you could memorize this, but you don't have to. You definitely should be able to look at the Arrhenius equation and reason that out, because you'll have the Arrhenius equation. But if you try to straight up remember and don't understand how to interpret this math, then you could get stuck, and you don't want to get stuck. So this is showing the relationship between a rate constant and a temperature K for a first order reaction with a molecule called an ester reacting with water. You can see as the temperature increases, we have this exponential increase in the rate constant as described by the Arrhenius equation. And what is the verbal explanation here? So we were explaining it with math, but how do we explain it with words? Well, if we increase the temperature, this is going to increase the speed of the molecules, the kinetic energy or their average speed. This will lead to more frequent collisions, and more importantly, the fraction of collisions that are successful and reach the activation energy will increase. So it's like a double whammy. You have two impacts here. Number one, you get more collisions, and number two, of those collisions, more of them are going to be successful in moving on to react. This can be described by this distribution of the speeds of the molecules. So the speed is related to the collision energy here. So what happens is when you increase the temperature, you increase the average speed of the molecules. So this distribution shows you what the distribution of the speeds of molecules would generally be. You'll have a peak here, and this is like the average speed around in here. But some molecules will be going much faster and some molecules will be going very slowly. You can think of this as like when you break the billiard balls on the pool table. Some are moving real fast, some are moving slowly, but we're looking at the average speed of all of them. If we increase the temperature, we increase the average speed. So you can see here the average speed has increased, which basically spreads out this distribution. And the result is that a much greater fraction, as represented in red here, of molecules have enough energy to exceed the activation energy. So at the lower temperature, only a small fraction of these molecules had enough energy to collide and reach the activation energy. But when you raise the temperature, you significantly increase the fraction of the molecules that have sufficient energy to react, because you spread out this distribution and you increase the average. So if the average is around here, you have increased the average. You've also significantly increased the number of high-speed molecules that have enough energy to react. So how can we calculate the activation energy? How can it be determined? It can be calculated directly, either algebraically or graphically, kind of like the way we did things for determining the order of reaction. We could determine it in various ways, one graphically, one just with only, math without a graph. So we have this activation energy here. What we can do is put this rate constant, we can do is put this into a linear form. This is the straight line form. How do we get that straight line form? Well, if you take this Arrhenius equation right here and you natural log both sides, you get the natural log of K equals the natural log of A e to the minus activation energy over RT. Now, from our algebra rules, you may remember that if you have the natural log of two things multiplied, that's the same as the separate things added. So we get natural log of K equals natural log of A plus e to the minus EA, natural log of, sorry. Forgot my natural log there. And plus the natural log of e to the minus EA over RT. Well, if we take the natural log of e, that gets rid of the e. So now we have the natural log of the rate constant equals natural log of A, and we have a minus here, so it's minus EA over RT. And now if we just separate out the t, we just move the t over by itself, we get this equation right here. And so this is a equation in the form of y equals mx plus b. Natural log of K is graphed on the y-axis, and 1 over t is graphed on the x-axis. And then the slope will be negative EA over RT, and the natural log of A will be b here. And so this is the straight line form of the Arrhenius equation. And it's in the y equals mx plus b form. Okay. If it makes you more comfortable, we can reverse where the natural log of A is. We can say ln of K equals negative EA over R T, 1 over T plus the natural log of A. So the natural log of A is the B. Again, the ln K here is the Y, the 1 over T is the X, and then the negative activation energy over R is the slope, and the natural log of A is the y-intercept. And so that's the way we can determine it graphically. Or if the data is available at two different temperatures, we can basically take one of these for the first temperature and subtract it from another one, and we get this altered form of the equation. And it's ln K2 over K1 equals negative activation energy over R times 1 over T2 minus 1 over T1. And this equation I would give to you if you need it. You don't need to memorize it. One exercise you could do, I don't want to go into it, but basically if you subtract one of these from the other, you'll get this. If you call one K1 and T1 and then you subtract it from another one with natural log K2 and 1 over T2, you'll get this equation here. And because you're subtracting a log, that's like dividing them. So you're comparing how big one is to the other, essentially. So graphically, if you want to determine the activation energy, and we did an exercise like this in the experiment B last week, you could have natural log of K plotted on the y-axis, 1 over temperature on the x-axis, and you'll get a line here with a negative slope, which is negative activation energy over R, and the y-intercept will be the natural log of A. So that's one way you can determine the activation energy. The other is by using the second equation that we saw, where you have the rate constants at two different temperatures here. And so here we can see we have a reaction decomposition of hydrogen iodide into hydrogen gas and iodine. It has rate constant 9.51 times 10 to the minus 9 liters per mole per second at 500 K and 1.10 times 10 to the minus 5 liters per moles per second at 600 K. Find the activation energy. Okay, so we've got two rate constants, two temperatures here. We're going to call K1, and it doesn't matter which one you call 1 or 2, just be consistent. 9.51 times 10 to the minus 9. And I'm going to write the units the way I like this. I'm going to say molars minus 1, second minus 1, because liters per mole is the flipped of molars, flipped of moles per liter, so molar minus 1. And T1, the K at this temperature is 500 Kelvin. And then K2 is going to be 1.10 times 10 to the minus 5. Molars minus 1, second minus 1, and T2 is going to be 600 Kelvin. So now we're going to use this comparative form of the Arrhenius equation, ln K2 over K1 equals negative EA over R 1 over T2 minus 1 over T1. And we're going to solve this for the activation energy. So we're going to have to multiply both sides. We want to get rid of the negative R, so we're going to multiply times negative R. And we also have to get rid of all of this. So I'm going to multiply this times 1 over T2 minus 1 over T1 to the negative 1 power. Okay, and so what's going to happen here is the negative will cancel. The R will cancel. And then this whole thing will cancel here, like that. We're going to do this, multiply times the same thing on the other side. So we're going to have negative R times 1 over T2 minus 1 over T1 to the negative 1 power. And so we've got activation energy equals negative R ln K2 over K1 and then 1 over T2 minus 1 over T1, and this is going to be to the negative 1 power, or 1 over this whole thing. And so now we're ready to plug in. And remember, when you plug in, to keep all of your units so you don't get confused. Our R is a constant, 8.314 joules per mole per Kelvin. And then it's going to be times the natural log of K2, which was 9.10 times 10 to the minus 5, molars minus 1, second minus 1, over K1, 9.51 times 10 to the minus 9, molars minus 1, second minus 1, times 1 over 600 Kelvin, which is T2, minus 1 over 500 Kelvin. And this is, don't forget, to the -1 power. Okay, so if you've got a single line calculator like I do, you're probably going to have to break this up into parts. You can, if you have a double line calculator, you may be able to punch it all in at once. This is really up to you how you want to do this, but whatever you do, keep track of the units. So here we should note that our molarities minus 1, second minus 1 are going to cancel here. And then on our next line, we're going to have equals -8.314 joules over moles Kelvin. All right. Oh, I'm in black here. Oh well, that's fine. Natural log something. So let's figure out what's in the natural log, just to make things easy on ourselves. So 9.1 e -5 divide 9.51 e -9 equals, we get, and I should keep at least 3 sig figs here, so it's going to be 9569, let's say 9569, where the 6 is the last sig fig. There are no units, the units canceled. And now this is where it can be tricky. Be very careful about the way you enter something like this. You have to do the division first before you do the subtraction. So I'm gonna do this with parentheses. So 1 divide by 600 minus 1 divide by 500 equals. Okay, and notice I get a negative. I do get a negative value, which is going to cancel our negative. And so we're going to get -3.333 and these, by the way, have 3 sig figs. You should be careful about your sig figs. We'll probably end up with 3, but you're subtracting, so the sig fig rules apply here. Maybe I should do that off to the side just to show you. So 1 divide by 600. So this is going to be, so 1 over 600 equals 0.001660. 0.001667 with 3 sig figs is this. And 1 divided by 500 equals 0.00200. Okay, and the last sig fig is here. So they're both at this place right here. We're actually going to end up with 2 sig figs in the end when we subtract this, because when you subtract it here, when we subtract these two, as we did, 0.02 minus 0.001667, we're only good here to the Whoops, I did that wrong. 0.002 minus 0.001667. So here we're only good to 5 after the decimal. So actually our last sig fig is this 3. So if we convert that back to scientific notation, though, it's going to be the second 3. That is our last sig fig here. I want to underline it. That's the last sig fig right there. That was times 10 to the minus 4. And our units are inverse kelvins, Kelvin to the minus 1. So you can see what's going to happen with kelvins here now. Our Kelvin units are going to cancel. So we have Kelvin divide by Kelvin essentially here. So those cancel. So all we have left for units are joules per mole, which is exactly the units we want. And so now we can probably pretty easily multiply the rest of this. So we're going to have the the 9569, take the natural log of that. So I did this part right here, put it in, times 3.33 EE minus 4 times 8.314. And so we're going to get a result with 2 sig figs. It's going to be, let's see, 2. I got a very small number here, which I didn't expect. Let's see, did I do something wrong? Oh, no, yeah, that's good. That's good. Let me double check here. I have my answer on the next slide. Oh, did I mix these up? That's what happened. No? Oh, I forgot to put this to the minus 1 power. Very common mistake. So even I did it here. Don't forget, this is to the minus 1 power. So I'm going to have to put that to the minus 1 power first. Oops, okay. I knew there was something wrong. So a joule is already a small amount of energy. That's how I knew when I got this number. I knew it couldn't be that small. Joule is already a small amount of energy. So I forgot to do the inverse of that. Okay, so I'm going to do, again, 9569. Take the natural log of that. So I have that. I'm going to multiply times 3.33 E minus 4. And I'm going to do 1 over that. And then I'll multiply times 8.314. Okay, there we go. And I get for my result, I'm running out of space here, but I'll write it up here. It's going to be 2.3 times 10 to the 5th. 10 to the 5th. And my units are joules per mole. Or joules is fine too. The mole would be understood. And so, yeah, so that's how you do it there. We did the algebra here to solve for the activation energy. If you want to plug in the numbers first and then solve for the activation energy, that's okay. Personally, I just think it's cleaner to do my algebra first and then deal with my numbers. But really, you know, that's up to you. Either way is fine. You don't have to solve it algebraically. You could plug in at first if you want to. And so then I plugged everything in, and the hard part is punching it into your calculator. So you're going to want to practice this. And I did give you problems where the answers are in the back of the book. So if you're not getting the same number, you should let me know at office hours. I did get a little bit different of a number here, 1.76. Why did I get something different? I'm going to use a double line calculator now and punch this in. One other thing I wanted to mention is that you may be wondering what happened to the negative sign. So there's a negative here, there's a negative here. So they cancel with each other. And so that's why that was different. I'm going to use my double line calculator just to show you guys, because probably you guys have a double line calculator, I imagine. And so just so you can see how you could plug this all in all at once if you wanted to, I'll show you that too on the Casio. So we could do negative 8.314 times the natural log of 1.1 times 10 to the negative 5 divide by 9.51 times 10. That's the EE or EXP button on this one. It looks like times 10, but you don't never type times 10 to the power, remember that. Okay, so that's our whole natural log there. We've done the whole natural log part. Okay. And now we're going to do times 600. I can call this 600 to the minus 1 power. That's a little trick for you too. That's 1 over 600 minus 500 to the minus 1 power. Then I close the parentheses and I take the whole thing to the minus 1 power. Now I bet you my answer was different because of my rounding in between, and there it is. So I did some heavy rounding in between, and that can mess with your result a little bit, especially when you don't have many sig figs. We only had 2. So if your answer is slightly different, it might be okay. Or maybe I just made a mistake somewhere in there, but here I punched it all the way through, and so you could see that this was the answer. It does kind of concern me what happened on the last problem, but I don't want to drag this out too much. Most of you guys have a double line calculator, so I would recommend you do it that way, but you can break it down into pieces just the same way I did there. Just remember, if you round too much, be careful about rounding too much, because it can really throw your answer off when you're doing a natural log. And so that's how you determine the activation energy using the Arrhenius equation, this 2-point form. So that's it for kinetic theory. In my next video, I'm going to be talking about reaction mechanisms, and that will be there'll only be 2 videos for this week, a little bit shorter of a week. So I'll see you in the next one. Okay. Bye-bye.